we mean that f and g do not factorize or have any. So if you expand f and g in terms of all possible polynomials in the base which lie in that class, and you take random coefficients in front of those polynomials, this would be maximally generic. So there would be no factorization, or there would be no relation between polynomials of different degrees, of course, but of different types between f and g. You just pick a random such polynomial.
Timo, just one small comment. I don't mean
well, I do not want those, because then we would not have a smooth elliptic vibration. Yes. Yes. So that is precisely what will happen when, right. And as we said, we can now see what happens in the various codimension, even though in this case the vibration will be smooth as such. So the generic fiber is just the smooth elliptic fiber. Over the discriminant, when the discriminant delta vanishes, but f and g do not vanish in codimension 1, we have a nodal curve. And in codimension 2, this can enhance to a cuspidal curve of type 2. We described the gauge group both in the M-theory compactification and in the dual F-theory. In the M-theory compactification, the gauge group comes by expanding C3 along all the elements of H11 of the vibration. We have H11 from the base plus 1 extra from the section, so we have a gauge group U1 to the H11B plus 1. But we argued that in the lift to F-theory, this gauge group goes away, so there is no gauge group in F-theory, because this becomes, or it's just a remnant of the tensors in F-theory from C4 along the two forms on the base, and this is the Kaluza-Klein U1 in going from F-theory to M-theory by doing a circular reduction. More questions? No, the line bundle L is something entirely on the base. It is, as we said, it's the anticanonical bundle on the base. So C1 of L equals C1 of B.
So where does the actual degrees of freedom inside these gauge groups go? Limit? Do they just get absorbed into the various other Ramon fields?
So this one becomes, as we discussed, part of the tensors in 2 dimensions. In F-theory. So C4 along the two forms gives me a tensor field. The tensor along the one cycle gives rise to a U1, to a gauge field, to a vector in 1 dimension lower, which is the M-theory. And this one is the Kaluza-Klein U1. So it has no, it is, just the Kaluza-Klein U1 by going, for example, from 4 to 3 dimensions. Okay. So this was really just the prelude. What we really need to worry about are the physically interesting cases of singular vibrations. So situations where not only the fiber becomes singular, but also the full manifold. And we'll start by looking at the codimension 1 behavior, because this is in 1-to-1 with the gauge algebra in M-theory, modulo this, and then also in F-theory. So now let us assume f and g are non-generic, so factorizations or other features can happen, which we will be discussing in a second. So for non-generic f and g in suitable class, the fiber degenerates beyond those cases, further, so beyond those cases above, and also yn plus 1 becomes singular. At points in the fiber over codimension 1. At a point in the fiber over the discriminant delta, which is a codimension 1 locus. And this type of behavior was famously classified by Kodaira and Neron, first for elliptic surfaces, so complex 2-dimensional, so n equal 1, and then further by Miranda in complex codimension in complex dimension 3, and this is, to my knowledge, believed to be the full story, and for good reason, also in 4 dimensions. So Kodaira and Neron, and then also Miranda, have classified the possible degenerations of a Weierstrass model with the following property: those degenerations which lead to a singularity in codimension 1, which can be resolved such that the resolved smooth space is Calabi-Yau and admits a flat fibration, meaning that the fiber in codimension 1 has everywhere that the fiber has everywhere complex dimension 1 up to codimension 1. So so we have classified the possible or the allowed degenerations of a Weierstrass model over codimension 1. Loci on the base with the following property: there exists a resolution yn plus 1 hat, a resolved space, which is a resolution of yn plus 1, which means it coincides with yn plus 1 everywhere except at the singular loci. And the singular loci are replaced by something else on this space, which makes the space smooth, Calabi-Yau, and a flat fibration. So there exists a resolution of the codimension 1 singularities such that yn plus 1 hat is Calabi-Yau, is also Calabi-Yau, actually I will not put this as a condition because it's automatic. What's important is really is a flat. It's true, but it's not the condition. It comes out. The condition is that we have a flat fibration in codimension 1. Meaning that this new space has fibers which are all of complex dimension 1. So the dimensionality of the fiber doesn't suddenly jump, at least not over codimension 1 loci. Fiber is one-dimensional everywhere, including in codimension 1. So what happens in codimension 2 is not clear in this classification, but up to codimension 1 at least. So more precisely, Kodaira-Niron classified singular elliptic surfaces, so the possible resolutions of Y2s with that property. And there, this flatness condition is the condition that the fiber contain no -1 curves for the experts. And Miranda then extended this to Y3s, including this flatness condition. And it's typically assumed that on Y4 and Y5, the same pattern is indeed exhaustive. So what is the result of this classification? The result is that the resolved space in codimension 1 has fibers which look like, in a sense we will discuss, like the extended Dinkin diagram of the simple Lie algebras. So with few exceptions, the resolved fibers, the resolution of the singular fibers in yn plus 1 takes the form of an extended Dinkin diagram of an ADE Lie group, Lie algebra, locally So over each point, locally, the fiber looks like the extended linking diagram of an ADE group. In Y2, this is already sufficient. And then in higher dimensions, there can be monodromies along the codimension 1 locus, which identify various components of this linking diagram, such as by this folding procedure, one globally arrives at extended linking diagram, also including the non-simply laced groups. So for yn plus 1 n bigger equal 2, monodromies along delta can lead to identifications, can identify some components of the resolved fiber and this way one also gets the non-simply laced groups, or algebras rather, Bn, Cn, F4, and G2. So combining these two, one arrives at a one-to-one correspondence between the extended linking diagrams of the simple Lie algebras and the structure of resolved fibers in codimension 1 of a Weierstrass model. So let's look at this. So this will be, or is already online in the notes, so don't take notes now, but just to show you what this classification is. So this classification proceeds by determining the order of vanishing of F, G, and delta over a particular locus, and then gives the local fiber type. This is just the name in Kodara's classification. The local resolved fiber, so the resolution and its local structure. Local meaning not take into account those monodromies, which complicate things. And okay, and let's first focus on this. So the first three cases were cases where where F and G are maximally generic, and these were the situations where we do not have a singularity of Y as such, of the fibration as such, only of the fiber. And the cross denotes the intersection with the zero section. So this is just symbolically for these fibers. Now what can happen? We see, for example, if F, G, and delta vanish to this order, F vanishes to order 1, G to order 2, then automatically delta, which is F cubed plus G squared, vanishes to order 3. And it turns then out that the fiber is singular, such that you can resolve. But once you resolve, you get in the fiber two curves. So the fiber now has, the resolved fiber has two components which touch in a double point, and one of those curves is still intersected by the zero section, and the other curve is a new curve. So we have the fiber to begin with, which is intersected by the zero section. This component will always stay, and then you have to add new P1s, new such curves, in the resolution process. And here you have to resolve by adding precisely one new P1, such that it will turn out that they intersect in one point, but at a double point. If you go on further, you get so-called type 4. Now you have to add two P1s, this one, and it turns out they will also intersect in one point. These are, so to speak, outliers. These are not written in this way, the affine linking diagrams of any group. But nonetheless, the self-intersections of the fibril curves, and I'll be more precise in a second, mimics, in this case, the Cartan matrix of group SU2, and here of group SU3. We'll discuss this in a second what this means. I'm just giving those groups already. And then we can go on in this classification. For example, there's now an infinite series. So these are the two exceptions I mentioned, with few exceptions. And now the rest is really in one-to-one with these ADEs. So here, for example, the IM series, if F and G do not vanish, but only delta vanishes. So F and G have no zeros, but the sum F cubed plus G squared vanishes, but not to first order, but to higher order. Then we have these IM fibers. And in this case, it turns out we have to include M minus 1 extra P1s to do a resolution. So this here was the old P1, the old fiber. And then we get M minus 1 new one. So altogether we have M components. And they intersect in this way. And this is precisely the affine Dynkin diagram of the gauge group, of the gauge algebra SUM-1, or A tilde M-1, the tilde for extended. And we can go on. So here we would have then a Dynkin diagram of D2n corresponding to SO4n, a special case being this. And we also have the E6, E7, and E8 series. So affine Dynkin diagrams of E6, E7, and E8. So these are the full ADE lists. And then, though I will not discuss this in detail, there can be global identifications due to monodromies, which then give rise also to these non-simply laced groups, for example, the G2 or the F4, and also the SP and the odd SOs can arise in this way. So we don't need all the details for now. You can look at the details there. I'll also give you the references if you really want to go through each of them step by step. What's important for us is really this statement that here we have this extended Dynkin diagram of the ADE groups locally at least. Maybe I'll put this on like that, and then the E8 is on the next page. Okay, and I'd like to explain this more, in particular also what's meant by this extended Dynkin diagram and where the physics comes about. So this was just flashing the results. I'll now go into more details. Do we already have questions now? But there's much we need to still discuss on this.
It's like the intersection between the nodes.
It's the nodes, very good, thank you, yes, I'll do this. So the nodes are the lines. The lines are the nodes. And the intersections are the way how they intersect. But precisely this will be I will discuss now. So for simplicity, we focus on fiber type ADE. So I don't want to describe these monodromies in class because they are just a complication, but not relevant for us. But you can, for example, look them up in detail in this work. This is not the original work, but it explains it very nicely. Where these for the non-simply laced cases. So the general situation is that our discriminant delta, the locus in the base over which this happens, now takes the following form. It splits into various components. And such that over each component delta I of the discriminant, the fiber is of ADE type as above, or as given here. So we would have the situation that we have here a base. Oh, no. Not so good. That we have here a base. This is the base Bn, and the discriminant will now contain various components. This is the discriminant, so this would be delta 1, delta 2, and so on and so forth. And over each discriminant locus, the fiber takes a particular form. So, for example, let us look at a fiber of A3 type in that language. I'm now drawing it slightly differently like this. So this notation is now more reminiscent of the Dynkin diagram. So every circle here represents one of the lines over there. So this is, so to speak, this object. Right? Yes. So 1 here, and then 0, 1, 2, 3. This would be here 0, 1, 2, 3. So they're the components are drawn as lines. This is how it's done in algebraic geometry, but this is more reminiscent of what they actually are, because the various components are really rational curves, P1s, and they form the nodes of the affine Dynkin diagram. So the fiber contains the following components. Each of those components is a rational curve, a P1. So there's P1, 0. This is the remnant of the original fiber, which is by definition the component which is intersected by this section. This is the remnant of original fiber. It's intersected by the section. In one point. And then we have the further P1s, which correspond to everything not intersected by the sections. And the number of those equals the rank of the gauge algebra whose extended Dynkin diagram the fiber represents. So here we would have gauge algebra A3, which would be SU4 of rank 3. So we have 3 such P1s. Yes, please.
What will happen if this section is intersected with around the
This does not happen in codimension 1. Because the zero section, because the singularity sits at the point x equals y equals 0, and this is and the zero section is 1, 1, 0. So the singularity is at x, y, z equals 1, 1, 0. That's where the singularity sits. Sorry, 0, 0, 1, like this, and the section, that's where the singularity sits. And the section is z equals 0. So this is 0, 1, 1. This is the section. So the singular point sits away from the section. And then what we do by resolving is we replace the singular point by a bunch of P1s. So that's why the section will not intersect it in codimension 1. Maybe I should write this. Okay. i.e., the resolution is really the following procedure. We started with, let me write it like this, the singular fiber. This was the singular fiber of y n plus 1. Here is the singular, this is the singular point. The section intersects elsewhere. And then the resolution is we replace this singular point by, in this case, 3 P1s on y n plus 1. So we have replaced this point by those 3 P1s, which then intersect the remainder, the affine node of the Dynkin diagram. Okay, I think I can remove this now. So we see the appearance of gauge algebras in the geometry in that sense. And of course the question is this a coincidence, or where does it come from? Or what's the physical meaning behind this? Thank you. Perfect. Thanks. And clearly these gauge algebras, which are imprinted into the resolved geometry, will be precisely the gauge symmetries in F-theory. And to see how this comes about, let us analyze the consequences of this vibration structure a bit further. So each of those P1s, each of those so-called resolution P1s, is fibered over the corresponding component of the discriminant. So we have a vibration P1I over this locus in a total space which I call EII over the component of the discriminant delta I. This, how much dimensional is this? So the discriminant delta is codimension 1 in the base. This here fills the full fiber, so this fibration is also codimension 1, but in the full fibration. So this is just a divisor. So this is a complex codimension 1 cycle on yn plus 1, i.e. a divisor called resolution divisor. And now this should ring a bell when we start thinking about gauge algebras. We said the gauge algebra in M-theory comes by expanding the M-theory 3 form along harmonic 2 forms. Harmonic 2 forms are Poincare dual to divisors. We in fact used this last time. So we can use it again. Now we have a new type of divisor which we didn't see before. These resolution divisors. We take their Poincare dual, a 2 form. These are harmonic such 2 forms because this is everything nice holomorphic, has no boundary, and is not a boundary. So we get new 2 forms and therefore new 1 forms by expanding C3 along them. So we can define a dual 2 form EII, and these are in fact harmonic. So what we are learning is, as is obvious, that the resolution process going from the singular space to the resolved space increases the number of 2 forms, of harmonic 2 forms, by precisely the rank of the algebra associated with this extended Dynkin diagram. So H11 of our resolved space still contains H11 from the base, and it still contains the 0 section. This was the 0 section, this was from the base. But now in addition, we have to add those resolution divisors, and there are rank G many. Yes?
How should I think about this resolution? So you want to just, right?
That's right.
So put
I replace the singularity. I do a blow-up, yes. I replace the singular point by a sphere, but such that the old space intersects that sphere in such a way, in the same way as it intersected, so to speak, the singular point. Right? So I replace the singular point simply by a bunch, by a chain of spheres. And so put differently, so given a singularity, one can do this blow-up procedure and put in spheres. And depending on how bad the singularity was, we have to put in a certain number of spheres. So in the simplest case, 1 sphere is enough, but more complicated situations require more spheres. And then and the structure of the singularity is equivalent to the intersection structure of those spheres after complete resolution. And in this sense, the singular fibers are classified by the result of this resolution process.
at first because we singularity was called.
That's right. It was a point in the fiber. So
That's why we can put a sphere around. So
exactly.
another codimension.
Well, we'll talk about higher codimension later. So as it turns out, in good cases, this already resolves also higher codimension singularities. It would work also in higher codimension, in principle. But it will turn out that we first have to do everything in codimension 1, and then either the resulting model is sick and you can't do anything about it, or it's already everything is resolved. So you will not have to do surgeries in codimension 2 explicitly. But we'll discuss this. Okay, so those are the divisors, and and of course from this we can already anticipate that we can now expand C3 as some I, some II, plus then all the further expansions that we already did. We don't take care of these anymore. This is just the new. Gives rise to new massless vector fields. By the same logic as last time. Yes, please.
The original P10 also
That is right, but that one we have already taken care of, because this one is essentially the zero section. Good point. So good point. Note, we have a relation that under the fibration, the inverse image of delta I as a divisor is the sum over I EII plus E0 I. So in other words, this is a relation that in fact is already, it's essentially the statement that this is the affine, that the P1 in there is the affine node of the Dynkin diagram. In any case, it's true. So the E0, the affine node, we can replace by the pullback of by a pullback divisor from the base, and those which we already have. But the pullback divisor from the base we already have taken care of, because this was essentially one of the H11 Bn many. It was not the zero section. I said it wrong. It's the pullback divisor from the base. So this one does not give rise to a gauge group in F theory. It's part of this gauge group in M theory, which then goes away in the F theory limit. So that's why it's only sufficient at this step now to worry about those. Thank you. So only EII gives new fields. So we can probably already guess what these fields are. These are precisely the fields associated with the Cartan U1 of these algebras. And I'd like to make this more precise. And first note a second fact. So as a matter of fact, we can now consider the intersection between those resolution divisors and the resolution curves. So a curve is dimension 1, a divisor is co-dimension 1. So altogether, the dimension adds up to the full dimension. So we have a well-defined intersection. The divisor and the curve intersect in points. And one finds that EII intersected with P1 JJ, say, that this is precisely minus delta ij times CII CJ. Where the Cij is the Cartan Cartan matrix of the gauge algebra G. The product is the intersection product between a divisor and a curve. The geometric intersection product. So for example, you have a two-dimensional space and a one-dimensional space inside a three-dimensional space. They intersect in points. It's a transverse intersection. And this is because this is a curve and this is a divisor. So codimension 1, dimension 1 adds up to codimension 0, i.e. point. Yes. Exactly. You take the dual volume form here. This is an n-1 form. This is a this is a 1 form. So this is a 2 form. This is a 2n-2 form. You get a 2n form, n being the complex dimension. You integrate it to a number, preset it. So maybe I should write it like this to make this connection with the forms also. Okay. So is it clear? Should we revise quickly what the Cartan matrix is? Or is that clear to everybody? Revision? Quick revision. Okay? So let's do a short group theory recap. So we are seeing here that really the geometry, even without knowing the details yet, the geometry really incorporates the group theory in one-to-one correspondence. So let's take G a simple Lie algebra. Then we can consider the generators, the maximally the maximal set of commuting generators of G is spanning the Cartan subalgebra. I equals 1 up to rank. By definition, these are the Cartan U1I generators, which are simply those as U1 subalgebras. They have the property that Ti with Tj equals 0. Okay, so this is the maximally commuting subalgebra. So they commute with each other, and therefore the remaining elements of the Lie algebra viewed as a vector space can be diagonalized with respect to them, as we know. So we can write Ti e beta equals beta I e beta for the remaining elements of the Lie algebra. For a basis of the remaining part of the Lie algebra G. So these are these E beta. And the beta I are precisely the roots. By definition, the eigenvalues with respect to this property. And now we know that we can form a basis consisting of the Ti, the Cartan elements, and then the positive and the negative roots, such that the positive roots are non-negative linear combinations of the so-called simple roots, and the negative ones with a minus sign. So we can form a basis Ti e beta plus, e beta minus of G, such that, I apologize, I write this here now, e beta plus can be written as non-negative linear combination of the so-called simple roots EI. Sorry, what do you call them? E alpha I. E alpha J, where J also goes from 1 up to rank G. And the E beta minus correspondingly with a different sign. So this defines the simple roots. So this defines our simple roots. Where J also goes from 1 up to rank G. And now the Cartan matrix is nothing other than the eigenvalues of those simple roots with respect to the Cartan generators. So Ti E alpha J equals Cij E alpha J. So Cij is the Cartan matrix. Or the root vector with respect to the simple roots, if you like, in that sense. And in particular, Cii, so on the diagonal, it's plus 2. That's the group theory normalization. And that's just nomenclature now, but since it's useful to have, the Ti are said to generate the co-root letters. Why? Because the E alpha I, these are the simple roots, and the co-root, that's the dual letters, because we have a non-degenerate pairing between the two given by this Cartan matrix. So the Ti, that's just jargon. We don't need this, but it's just jargon. Generate the co-root letters in the sense that we have a non-degenerate pairing between Ti and E alpha j to Ti E alpha j equals Cij is a non-degenerate pairing. Non-degenerate pairing, so this is kind of the dual space and the dual lattice. Can you read? The Ti generate the co-root letters due to this existence of a non-degenerate pairing in that sense.
So that's like an inner product.
Yeah, you can think of it as an inner product in this sense. You define it in this way. Okay, and now this is the group theory, in particular this one here. And we see beautifully how it is realized in the geometry. Obviously, we should now identify the Ti, which are the generators of the U1 subgroup, with these divisors via this relation of C3. And then the resolution P1s in the fiber correspond up to a minus sign to those simple roots, group theoretically, because the pairing, the intersection product, is to be identified with a group theoretic pairing. So let's interpret this physically. So we already had the vector fields from the resolution divisors. So the AI correspond to massless. These are massless U1II vector fields associated with the Cartan algebra of G. Why are they massless? Why are they massless? Exactly. It's a harmonic 1-1 form. Exactly. It's an H11 in the homology class. Very good. Thanks. So we get those gauge fields. And now there's a second physics input. C3 in the M theory, we said, couples to an M2 brane. So we can now consider M2 branes which wrap those P1s in the fiber. So an M2 brane has 2 + 1 dimensions. Wrapping it around a 2 real dimensional curve gives rise to a particle in the effective action. So wrapping an M2 brane on the resolution curves P1s gives rise to a particle. And the charge of this particle under U1I is precisely given by this Cij. So now we consider a wrapped M2 brane on P1I, P1J on a resolution curve. This gives rise to a particle in the effective action. So in R1 8 minus 2n in M theory, a particle. And its mass, what is its mass? What's the mass of this particle? roughly? This size of the P1, exactly. The volume of the P1 of mass m proportional to the volume of P1J.
Why is it relative volume?
Because the action of the M2 has two parts. It has it had this 2 pi over L cubed times square root minus determinant G integrated over the M2 plus the Chern-Simons part, and this is precisely the volume. So this is volume. The volume times the tension will give us the mass. Volume times tension will give us the mass. And second, it has mass given by the volume of this P1, and its charge is set by integrating the gauge field, the internal part of the gauge field, over the internal part of the M2 brane. Because as Chern-Simons we had was also 2 pi over L cubed times integral C3 over M2. So we can write this now as A wedge E over the M2 brane is R times P1J. So this is clearly integral over R AI times Q, where Q is EI over P1J, which is precisely this intersection product which is minus Cij. So we therefore see that we have this correspondence between the geometry, the physics, and the gauge theory, in the sense that, let me put this here. We have, in the geometry, we have our resolution divisors EI. They correspond to the co-roots Ti, i.e. the Cartan generators U1II, and the resolution curves P1J, these correspond to the simple roots, in other words, to states whose charge is Cij up to a minus sign, minus the simple roots Okay. Questions? Yes. Very good. We'll discuss this. Then you get a KK state because it is intersected by this 0 section whose associated U1 is the KK U1. We'll come to this. Good question. More questions? So we see that we get these particles from Repton 2 branes. In fact, the question is what types of particles are these? And what one would now have to do is one would have to quantize the moduli space of those particles. These are particles which have a moduli space. They can move over the discriminant. And arguments by Witten show that in this case one gets a vector and also a certain number of scalar fields out of these particles as well. So quantization of the moduli space of the rept M2 on P1J gives us then particles on the type of particle propagating along the extended spacetime R1 8 minus 2n times delta. That's the part of the discriminant over which we worked, and the argument is given. It's a sketchy argument, but it's a nice argument given in this paper, page 1314. And these particles correspond to, first of all, a massive vector of above mass m plus superpartners, of course, if we look at the supermembrane. And in addition, if the dimension of the discriminant is bigger than 0, so if it's not just a point but higher dimensional object, then we also get extra scalars, additional massive scalars. So we will describe in detail which type of massless matter, of in this case massive matter, still a same mass, of course, same mass m plus superparticles. We'll describe in detail which types of matter these are next time. So for now, let's forget about the scalars, keeping them in the back of our mind. We'll come back to this tomorrow and focus on the vectors. So focus for now on the vectors. We have established the presence of vectors associated with each simple root. We want to fill, or our endeavor is to fill, possibly the entire adjoint of the gauge algebra. So we know from our group theory that from the simple roots we can form by non-negative, positive or negative, by non-negative or non-positive contributions the positive or negative roots of the adjoint. So we can now form non-negative or non-positive linear combinations of P1II corresponding to the positive or negative roots, E beta plus and E beta minus. Wrapping M2 branes on those will give rise to the corresponding states, again vectors of scalars, in particular vectors of corresponding mass. So we populate in this way, populate massive vectors corresponding to the E beta plus and E beta minus. These are massive. But in the limit where the volume of all the p1s shrinks, so in the limit where we go back to the singular Calabi-Yau, the mass of those goes to 0, and we get massless vectors. As the volume of p1i goes to 0 for all of them, not equal to 0, not the 0 modes, these become massless. And in that limit, we recover the full adjoint representation of the gauge algebra, because we have the positive and negative roots as massless vectors. And in addition, we have the rank G vectors from C3. So we have at the massless level now the AI, and we have the A E beta plus and A beta minus massless. And these form the full adjoint of G. So in other words, in the limit where we shrink the volume of these resolution curves, we recover the full adjoint G of massless vectors. So in this limit, we have a gauge algebra in M theory whose algebra is precisely the one underlying the geometric structure of those singularities. Put differently, resolving the singularity means taking the volume of those curves from 0, where they are not there, to non-zero. This means that we make the vectors associated with the positive and negative roots massive. The Cartan vectors are not affected by this, because their mass is not governed by the volume of the p1s. So in that limit, so in that process, by resolving the singularity, we reduce the adjoint to only the Cartan subgroup. So this is precisely what's meant by the Coulomb branch, by going to the Coulomb branch of the theory. So resolution of yn plus 1 to yn plus 1 hat to the resolved space is equivalent to going to the Coulomb branch of gi in the dual in the M theory. And this completes or adds another line to our dictionary between geometry and group theory physics. Namely that the resolution P1s, these correspond to the simple roots. The resolution divisors, these correspond to the Cartan U1s, or the co-roots. And the volume of the P1s corresponds to the Cartan parameters, the Cartan branch operators, operators. Sorry, Coulomb branch, what am I saying? Coulomb branch. Because resolving the space breaks the gauge algebra to its Cartan in M theory. That's a crucial insight. That's an important insight, that resolving the singularity is equivalent to going on the Coulomb branch, in the sense described there. Yes, please.
So, critical to this story that you determined from this paper that you actually have masses of vector multiplets.
Yes, yes.
I'm just curious to learn, are you using details the M theory? Has a similarly thorough analysis been done in 3D? From other perspectives, one can get info.
I know, of course. Well, So Dave would say that they did something similar in their paper with yes. So that is maybe more on the field theory side, on the top. We can talk more. We can talk more about this. I have some ideas about that.
Okay.
More questions? Yes. Yes.
I just wanted to
Yes.
comment
Yes.
on the last question. I think that in KDE can be proven that the master of the algorithm should not be depend on the potential. So there is some subset that
So at tree level, the tree level mass is still the volume of those P1s.
from the empty perspective.
Yes.
Yes. So
Yes.
there is a P1 the remote cycle,
Yes.
M2, and then the master will be this one.
Yes.
But then there is an argument that equal to equal 4 central part.
Fine.
And this is the solution. The bottom of the if I think only grid should not be done question. Therefore, theory.
Okay, we need to talk about this later. I can't say no, but from to my understanding, these are the masses. Yeah. Okay, good. Let's discuss this. Great. More questions? Good. Yes. So, not naive at all, of course. The resolved. So this is why I underlined this here. I wanted to come to this still. So going to the Coulomb branch, that's something that happens indeed, as you point out, in the M theory. So in the dual F theory, the F theory is the limit where we take the volume of the elliptic fiber to 0. So in particular, we take the volume of the resolution P1s to 0. We do even more, but in particular, those of the resolution P1s. So in the F theory, we are automatically in the origin of the Coulomb branch, at least of that Coulomb branch that we described here. Okay. Oh yeah, that's right. It's here. Important. The F theory limit takes the volume of the full fiber, let me write it like this, to 0. So this includes volume of P1I to 0. It includes this, because the P1I, of course, sit in the fiber. So in the F theory, we are automatically in the origin of the Coulomb branch, at least the one described in this way. There might be a Coulomb branch also in the F theory, but that is then a different mode. That is then more a deformation of the brain from a brain perspective. So this Coulomb branch, this above Coulomb branch, is accessible only in M theory. Put differently, the M theory limit is a singular limit. This is the limit where the vibration really is a singular vibration. So also the resolution is something that is occurring on the M theory side and not on the F theory side. So in particular, the F theory limit, the F theory probes yn plus 1, the non-resolved. Space. So if you like, this resolution is an auxiliary procedure in order to gain information about the underlying space and to make those physical arguments. But at the end of the day, we have to take the singular limit in a controlled manner. And this is then what will give rise to the F theory. Yes, please.
Clarify terminology. We say resolution.
That's right. Yes.
Okay. So the F theory.
Exactly. Absolutely. Yes. because that would then correspond to, say, a change of the 7 branes in relative position. The relative position of the 7. And that's, of course, also something that can be considered. Like, I don't know if Jim will talk more about this, maybe, but the deformations as a possible.
I can comment, but I can comment.
Very good, very good. Okay, so another note I need to make, since this is also since this came up. So the question was, what happens to the M2 branes which wrap the extended node, the one intersected by the section? So these give rise to states which carry charge under the KK-U1 by going from F theory to M theory. So these are just the KK modes of the particles that we get by going from, say, 4 dimension to 3 dimension or 6 dimension to 5 dimensions. So since the 0 section intersects the P1s only in the 0 node for all I not equal to 0, and non-zero, so 1 for I equals 0, this shows that an M2 on P1 0 carries U1 KK charge, so more precisely, we can now take an M2 brane wrapping, say, P1 1, one of them. This gives rise to a state with KK charge 0. Now, to get the state of the same U1 charges, but in addition with KK charge 1, which would be the first KK excitation, we have to add simply the entire class of the fiber once. So more precisely, if we take a state on P1I plus n times the class of the full elliptic fiber, the full torus, this corresponds to the full tower of states psi n of KK charge n and U1 I charge minus Ci. So if we start, for example, from a field in 4 dimensions and circle reduced to 3 dimensions, we not only need to get the 0 mode in the 3-dimensional M theory, but also the full tower of KK states. And those KK states correspond to M2 branes wrapping the original P1 plus suitable copies of the full fiber. The full fiber is uncharged under the resolution divisor, so this one will not give rise to an extra U1 charge, as one can show. But it does carry Kaluza-Klein U1 precisely of unit 1. So this is how you can then recover the full tower of KK modes associated with these higher dimensional fields. It won't play much of a role for us now, but it's if one wants to go into the details of this FM theory correspondence, then this is something one has to take into account. Okay, so I wanted to present you an example, in particular an example of the resolution. Unfortunately, I do not have the time to present all of this in class, but it's written in detail in the notes, and I'll be happy to discuss this then also offline anytime. But at least I'll show you the easy part, just so you have these abstract concepts in formulae for a very simple example. And then you can see that it's really quite easy to read off all of those statements explicitly in the geometry. So I'll do this very fast. So an example would be resolution of an SU2 example. And again, all the details are in the notes. I'll be very quick. So we start with a Weierstrass form without singularities, but I'll give it to you not in Weierstrass form, but in so-called Tate form. So we start with Pt equals y squared plus a1 xyz plus a3 yz cubed minus x cubed plus a2 x squared z squared plus a4 x z6 plus, is that right? No, 4 plus z6. Yeah. So this is a Weierstrass model in so-called Tate form. This means that we can go back to the usual Weierstrass form from here by completing the square in y and the cubed in x. So we can translate back into Weierstrass form, standard Weierstrass form, by completing the square in y and the cube in x. You could do this as an exercise. And if you do this, then you find your f and your g as functions of these coefficients a1, a2, 3, 4, and 6. Function of ai, and g is a function of ai as well. And the ai's are now sections of the base powers of L. So f is something, for example, ai to the 4 plus then something with a4 and so on and so forth. In this so-called Tate form, there exists an algorithm for how to specialize f and g further, such as to precisely get those singularities that appear in Kodaira's list, and in fact also including the monodromies. And an example would be an I2 singularity corresponding to gauge algebra SU2 over some locus w equals 0 on the base V2. So this would come, the result of this algorithm, I give you the references, would be that we take A1 to be generic, but then the others have to factorize as follows. A to 1w, A3 would have to be A3 1w, A4 would have to be A4 1w, and A6 would have to be A6 to w squared. So this is precisely, 2 more minutes please. This is precisely this kind of factorization, in this case in the language of the AIs, that would give rise to a special structure of the fibers. And if you go back into the F and G with this ansatz and use the formulas after doing this little algebraic exercise, you will find that F goes like minus A1 to the 4 plus order W, and G goes like up to prefactors A1 to the 6 plus order W. So we see that there are special numbers in the front, and they are tuned in such a way that delta has a component which vanishes in order w to the 0 and has precisely terms coming with w squared. So if you plug this into the formula for delta, you get something like w squared times a rest. So we see precisely this factorization of delta. So delta factorizes into delta 1 times delta 2. This would be delta 1. This would be delta 2. In such a way that here we have vanishing order 0, 0, 2 for f, g, and delta, the order over this locus, and this precisely corresponds to singularity I2. And then you can look at where the singularity lives. You can do this explicitly. You can resolve it. It's in the notes, and I'll be happy to discuss it. And you will find precisely the structure of one resolution divisor needed in the fiber. So next time, we'll go from there and look at the higher codimension structure. And this will then also tell us something about the matter representations, the weight letters, and their interactions by going to codimension 3. More questions? Yes, on. Yes. Yes, L to the power of I. Indeed, thank you. Yeah, so I's tensor product of L. Indeed. Thank you.
So, A2 is also dynamical, right?
Say again?
A2 is also dynamical.
Indeed, so these here, the A21, A41, 62, A3 are generic, yes. There are two types of I2, a split and a non-split type. This is the split type. So SU2 is isomorphic to SP1. The split type is the SU2. The non-split type is the SP1. And they differ in codimension 2. So the non-split type, the SP1, the one where this is generic, has extra monodromies that show up in codimension 2. So this is indeed the split version, which is I2, so split version. And there it has a 1 in Kodaira's table. Not in Kodaira, this is Tate's table, in fact, which takes into account those monodromies. Yeah.
I have a very simple question. Why are you allowed to do it? You're changing the space.
Okay, good. Good, yes. So I'm allowed to do it in the sense that it's a flat direction. So it's a modulus that I can turn on. We should think of this, the singular space, as really a singular as a point at the edge of the moduli space of Calabi-Yau's, at the origin, so to speak. And since it's a modulus, I'm allowed to move into other directions. So, but I agree with you that it's only an auxiliary construction in order to deduce the physics by saying, okay, we first resolve, we look at the states, the matter that we have there, and then we go back and take the limit that we are actually interested in. And this procedure is okay as long as the direction along which we go is a flat direction. So as long as we don't break supersymmetry, this is a controlled, continuous process to do. So it's, from the perspective of F-theory, it is an auxiliary construction.